In the last lecture I introduced psychrometry, and where we discussed important psychrometric properties, and we also introduced the concept of thermodynamic wet bulb temperature, and we also discussed the psychrometric chart. It is seen that fortunately for air water mixers, the thermodynamic wet bulb temperature can be measured with sufficient accuracy using a wet bulb thermometer, provided certain precautions are taken, and I have also mentioned what are the precautions to be taken. And I also mentioned in the last lecture that a psychrometer is an instrument using which one can measure the dry bulb and wet bulb temperatures of moist air simultaneously. And there are basically two types of psychrometers. One is what is called as a sling type of psychrometer. The other one is known as aspiration psychrometer. One of the important requirements while measuring wet bulb temperature is that there must be a relative motion between the wet bulb and the surrounding air. That means either the bulb should be moving or the air should be moving. There must be some relative velocity. Okay. In a sling type psychrometer, which consists of a dry bulb thermometer and a wet bulb thermometer, the thermometers are rotated, which creates a motion. Okay. So the rotation of the thermometers creates a motion, and this will give the correct reading of the wet bulb temperature. In an aspiration psychrometer, a small fan is used. This fan draws the moist air from the surroundings and blows the air over the wet bulb thermometer. Thereby one can measure the wet bulb temperature accurately. So it is very important to keep in mind that while measuring wet bulb temperature, one has to take certain precautions only when the temperature indicated by the thermometer will be close to the thermodynamic wet bulb temperature. Now, having measured wet bulb and dry bulb temperatures, next task is to find the other psychrometric properties such as enthalpy, humidity ratio, etc. Okay. So for this we have to use certain empirical relations which will relate the wet bulb and dry bulb temperatures to the vapor pressure of water. Okay. So I will show these equations in this lecture, and I also discuss important psychrometric processes in this lecture. So the specific objectives of this particular lecture are to present empirical equations and discuss calculation of psychrometric properties using psychrometric charts and equations, discuss important psychrometric processes, and finally describe air washers. At the end of the lecture, you should be able to calculate psychrometric properties using either psychrometric charts or psychrometric equations, analyze important psychrometric processes and perform necessary process calculations, and explain the working principle of air washers. So first let us look at calculation of psychrometric properties. As I have already mentioned, using a psychrometer one can measure both the dry bulb and wet bulb temperatures, and one can also measure the barometric pressure, for example using a barometer. Okay. So once we know the barometric pressure and the dry bulb and wet bulb temperatures, how do we find the rest of the properties? First task is to find out the vapor pressure. So the vapor pressure can be obtained by using any of the empirical relations shown below. Okay. For example, one can use a relation called modified Absorption equation. This is shown here, where PV is equal to P dash V minus 1.8 P into T minus T dash divided by 2700. In this equation, PV is the vapor pressure of air. P dash V is the saturated vapor pressure at wet bulb temperature. P is the total pressure or barometric pressure. T and T dash are dry bulb and wet bulb temperatures respectively. Here units are important. Dry bulb and wet bulb temperature should be in degree centigrade, and the pressure unit should be consistent. So this is one of the empirical relations using which one can find out the vapor pressure. For example, here we know the dry bulb and wet bulb temperatures from the psychrometer readings. Then we can find out P dash V, which is nothing but the saturated vapor pressure, using steam tables or equations for saturated steam. Then barometric pressure is anyway known. Okay. So next empirical equation is what is known as modified Ferrel equation. This equation is given by PV is P dash V minus 0.00066 P into T minus T dash multiplied by 1 plus 1.8 T by 1571. Again here T and T dash are dry bulb and wet bulb temperatures. P is the barometric pressure. P dash V is the saturated vapor pressure at wet bulb temperature. One can also use what is known as a carrier equation suggested by Willis carrier. This equation is shown here. PV is equal to P dash V minus 1.8 into P minus P dash V into T minus T dash divided by 2800 minus 1.3 into 1.8 T plus 32. As I have already mentioned, in all the above equations, T and T dash are the dry bulb and wet bulb temperatures, and the units must be in degrees centigrade. PV is the vapor pressure, P dash V is the saturated vapor pressure at wet bulb temperature, and P is the barometric pressure. And as I said, all the pressure units must be consistent. Okay. So these empirical equations can be used, and using these empirical equations one can find the vapor pressure. Okay. Now let us look at calculation of psychrometric properties. From given barometric pressure and any two psychrometric properties, one can calculate all the other psychrometric properties using either psychrometric equations or psychrometric chart. For example, using psychrometric equations, how can we calculate the properties? Let me give some examples here. So calculation of psychrometric properties using psychrometric equations. For example, let us say we know the total pressure, dry bulb temperature and wet bulb temperature. These three are the independent properties, and using these three properties we must find the other psychrometric properties. So step 1 is from dry bulb temperature and wet bulb temperature, calculate vapor pressure PV using any of the empirical equations discussed just now, that means Carrier equation or Ozone or Ferrell equations. Okay. Then calculate rest of the properties using PT, PV and DBT. For example, what do we mean by rest of the properties? Let us say once we know the vapor pressure, all other properties can be easily obtained. For example, I want to find out, let us say the humidity ratio W. Okay. Assuming the moisture to behave as a perfect gas, we have derived the equations for the humidity ratio to be 0.622 PV divided by PT minus PV. Okay. So PV is known from the empirical relations, PT is the barometric pressure, PV is the vapor pressure. Okay. So you can find out what is the humidity ratio. Similarly, if you want to find out the enthalpy also we have obtained equations like this, CPA into T plus HFG plus W into HFG plus CPV into T. Okay, so here HFG is not there. So here, as you know, CPA is the specific heat of dry air, CPV is the specific heat of water vapor, T is the dry bulb temperature which is known to us, and HFG is the latent heat of vaporization which can be obtained from properties of steam, and W is the humidity ratio. So you have found the humidity ratio from the pressures, so substitute this W value here, we can find out the enthalpy. Similarly, one can find the other properties. Okay. Suppose we know, let us say the total pressure, dry bulb temperature and relative humidity, and we have to find out the rest of the properties. First thing we do is from dry bulb temperature value we calculate the saturation pressure using steam tables or the regression equation. For example, the Asher equation which was mentioned in the last lecture. Okay, so first find out the saturated pressure of water vapor at the dry bulb temperature. Then calculate vapor pressure from relative humidity and saturated pressure. Okay, because we know that relative humidity, if you are assuming ideal gas behavior, is simply given by RH is simply equal to PV divided by Psat. Okay. So Psat is a function of dry bulb temperature only, so this we can obtain because we know the dry bulb temperature. Okay. So Psat is known and relative humidity is mentioned. Okay. So then you can find out what is the vapor pressure PV. Once you know the vapor pressure PV, calculating other properties is very easy. Calculate rest of the properties using dry bulb temperature, vapor pressure and total pressure. Okay. So like that, using the simple equations mentioned in the last class and some of the empirical equations, given any three properties, remember that you need three properties to fix the state of the moisture completely. Okay. So using any of these three properties, you can find out the rest of the properties, right. So this is the method of estimating psychrometric properties using psychrometric equations. Okay. Now the same thing can be done very easily using the psychrometric chart. Okay. For example, in the psychrometric chart, I have also already shown this psychrometric chart in the last lecture, and I have explained to you what are the different lines. Suppose we know dry bulb temperature and let us say relative humidity. Okay. So for example, it is given that this is the dry bulb temperature and this is the relative humidity. Okay. So these two are given, and obviously the barometric pressure is also given. So one very important thing while using psychrometric chart is to make sure that you are using the right chart. Okay. That means you must use the chart given for that particular barometric pressure. Okay, so you must always look at the chart and see for what barometric pressure the chart is drawn and whether that barometric pressure matches with your barometric pressure or not. Okay, so once you make sure of that, then it can be used easily, right. Now, as I said, once we know the dry bulb temperature and relative humidity, let us say that relative humidity of 50%, let us say this is 50% relative humidity line, and this is some dry bulb temperature. So, we know these two values. So, the intersection of constant relative humidity line of 50% and the constant dry bulb temperature line gives you the point. Okay. So, first you locate the point. So, that point is this. Once you locate this point, all other properties can be easily read from the chart. For example, a humidity ratio can be directly read from here, enthalpy can be read from this value because enthalpy line is like this, specific volume is this. So, once you put the point on the chart, all other properties can be obtained. Okay. Or sometimes you may have for example, dry bulb temperature is given and humidity ratio is given. Okay, let us say that dry bulb temperature is this and humidity ratio is this. Okay, so you can fix the point by the intersection of the constant dry bulb temperature line and humidity line will give you the psychrometric point or state of the air. Once you fix the state of the air, other things can be easily obtained. For example, relative humidity will be something like this, and enthalpy value is this, and okay, so specific volume is between this value and this value. So you may have to do, of course, some interpolation when you are using the psychrometric chart. Okay, so reading from the psychrometric chart, even though it is easy, it can give rise to error if you are not reading the values properly, or if you are not doing the interpolation properly. Okay, so for calculation purposes, it is best to use the psychrometric equations, because which will give you the correct reading. Of course, in the absence of psychrometric equations, one can use the psychrometric chart. Okay. So this is how one can calculate the psychrometric properties. Now once we know the properties, next let us go to the psychrometric processes. This is a very important topic, psychrometric processes. In the design and analysis of air conditioning plants or air conditioning systems, the fundamental requirement is to identify the various processes being performed on air. Once identified, the processes can be analyzed by applying the laws of conservation of mass and energy. All these processes can be plotted on a psychrometric chart. This is very useful for quick visualization and also for identifying the changes taking place in important properties. Okay. So the summary is you must be able to know what kind of processes are being performed on air and identify the process properly and draw the process properly on the psychrometric chart. Okay. So this will give you an idea of what is happening during the process, what property is changing how. Okay, and if you are reading the chart properly, this will also give you the different changes taking place in the properties. So using the properties and then by applying the conservation of equations, one can estimate what is the amount of mass transferred or what is the amount of heat transferred, etc. during a given process. Okay, so the understanding of the processes is very important, and what we will do is we will be showing all these processes on psychrometric chart. Okay, we will show the process path on the psychrometric chart. Okay, so let us begin with the simple process. Let us look at some of the important psychrometric processes. The first process is a very simple process, that is sensible cooling. Okay, so as the name implies, during this process the humidity ratio of air remains constant, but its temperature decreases. Okay, that means there is no mass transfer, only sensible heat transfer takes place. Okay, that is why you call it a sensible cooling process. This can be achieved by bringing the air in contact with a cooling coil whose surface temperature is lower than the dry bulb temperature but higher than the dew point temperature of the incoming air. Okay, because you want to achieve only sensible cooling, you do not want to add or remove moisture from the air. Okay, that means there should not be any moisture transfer. Okay, so when you are bringing the moisture in contact with a cold surface, for example, and if the cold surface temperature is above the dew point temperature of air, then air gets sensibly cooled. Okay, that means no moisture transfer takes place. Okay, so that is what is required if you want only sensible cooling, right. Okay, let me show this process. So how we can show this process on the psychrometric chart. This is very easy because during this process, as I have already discussed, the moisture content remains same. So it will be a horizontal line because this is the humidity ratio or moisture content ratio, moisture content line. So the moisture content at inlet, like this is the inlet, this is the outlet. Okay. So, moisture content at the inlet and outlet remains same, so the line is a horizontal line, and the lines moves in this direction because air is being cooled, so air temperature decreases. Okay. That means TO is greater than TA obviously. Okay. This is a cooling process, right. So, you can very easily, once you identify this state and once you then put this state, then you can find out the rest of the properties if you are reading the psychrometric chart properly. Okay. Now, let us see what is happening during this process. As I said, the dry bulb temperature is reducing. Okay. Dry bulb temperature reduces, dew point temperature remains constant, because corresponding to this point or this point, the dew point temperature is this temperature. That means you have to draw this, extend this line, and where this line intersects this saturation curve, that temperature will give you the dew point temperature. Okay. So, this is your dew point temperature. Dew point temperature remains constant because moisture is not neither added nor removed. Okay. So, dPT remains constant. Then you can see that relative humidity is increasing. Okay. At this point relative humidity is something like this, at this point relative humidity has increased. Okay. This is because you are keeping the moisture content same, but you are reducing the dry bulb temperature. Okay. So, as a result relative humidity increases. Obviously, enthalpy reduces. Okay, because enthalpy lines are constant, enthalpy lines are like this. Okay, enthalpy increases in this direction. So, enthalpy reduces because you are taking energy from the air. So, enthalpy of the air reduces. Okay. So, like that you can easily visualize what is happening to air during this process, and you can also read all these properties, inlet and outlet properties, from the psychrometric chart. Now, the heat transfer rate during this process is given by QC is equal to MA into H naught minus HA. This is obtained by applying energy balance. This is the HO minus HA can be written as CPM into TO minus TA, where CPM is the moist air specific heat, TO and TA are the inlet and outlet temperatures, and here MA is a mass flow rate of dry air in terms of kg per second. Remember that this I have repeatedly told in the last class also. In all psychrometric calculations and all psychrometric properties are indicated on basis of dry air mass flow rate. Okay, I have already explained what are the advantages of using dry air as the basis. Okay, so MA is the mass flow rate of the dry air, right. Now, next let us look at another simple process, that is sensible heating process. Of course, this process is exactly opposite to the earlier sensible cooling process. So, during this process the moisture content of air remains constant and its temperature increases obviously, because you are heating the air. This can be achieved by bringing the air in contact with a heating coil whose surface temperature is higher than the dry bulb temperature of the incoming air. Obviously, you have to have a surface or a whose temperature is much higher than the dry bulb temperature, so that the air can get heated up. And how do you show this process? Very easy. This is a heating process, so temperature of the air increases. Okay. So, the process moves in this direction, and humidity ratio remains constant, that means the moisture content remains constant. Okay. Temperature is increasing obviously, TB is greater than TA. Again you can see that during this process relative humidity reduces, okay, because moisture content is remaining constant, relative humidity reduces. Okay. Enthalpy increases because you are adding energy to this thing, so enthalpy increases, right. Again dew point temperature remains constant, right. Like that you can find out the other properties and you can read the property values from the psychrometric chart. And similar to sensible cooling, the heat transfer rate during sensible heating process can be obtained very easily by writing performing energy balance, and QH is the heat transfer rate, that is equal to MA into HB minus HO, where HB and HO are the exit and inlet enthalpies of the moist air, and HB and HO can be written in terms of the specific heat and temperatures. That means finally you can write QH as MA into CPM into TB minus T naught, where CPM as I said is the specific heat of the moist air, TB and TO are the exit and inlet temperatures of the air. Now, let us discuss a very important process. This is called cooling and dehumidification. So, as the name implies, during this process air gets cooled and air also gets dehumidified, that means the moisture content of the air reduces. And how do we do this? What is the principle behind this? When moist air is cooled below its dew point by bringing it in contact with a cold surface, some of the water vapor in the air condenses and leaves the air stream. This we see from our day to day experience. For example, if you leave chilled cool drink bottle or chilled water glass of chilled water on the table, you find that on the outside of the surface of the bottle or on the glass water droplets appear. Okay, so where does the water appear from? So obviously water is coming from the surrounding air. If the temperature of the cold water or the cool drink is less than the dew point temperature, when air comes in contact with the cool drink or the water, moisture in the air condenses on the bottle or the water, okay, because its temperature is lower than the dew point temperature. Once moisture condenses, you are taking out the water vapor from the air in a liquid form. That means air becomes dried or air becomes dehumidified. Okay, so if you want to perform the process of cooling and dehumidification, what is required is you must have a cooling coil, or you must have a surface whose temperature is lower than the dew point temperature of the incoming air. Okay, so when air comes in contact with such a surface, not only air's temperature reduces because of the temperature difference, but its moisture content also reduces because some of the water vapor in the air condenses and leaves the air as in the liquid form. Okay. So as a result, as I said, both temperature and humidity ratio of air decreases. So how do we show this process? So although the actual process path will vary depending upon the type of cold surface, the surface temperature and flow conditions, for simplicity the process line is assumed to be a straight line. Actual process path line is quite complicated and it depends upon several factors, but we assume that the process is a straight line. Okay, so let me show the process. So this is how it is done. For example, you can see here, let us say that we have a duct, a cooling duct. Okay, this consists of a cooling coil here. Okay, for example, this cooling coil could be the evaporator of a refrigeration system. Okay, that means refrigerant flows through this coil, or it could be a chilled water coil. That means a chilled water flows through this. Okay. So when that means the coil surface, and as I said, the surface temperature of the coil is Ts. Okay, it is shown here. Ts should be lower than the dew point temperature of air. Okay, when it is lower than dew point temperature of air, and when this air comes in contact with the coil, some of the water vapor condenses. Okay, and it leaves in liquid form. So this MW is the what is known as a condensate. Okay, condensate is nothing but the liquid water that has condensed from the moist air. Okay, and once it condenses, it leaves the air stream. Okay, so what is coming out from the duct is condensate and cooled and dehumidified air. Okay, so you can see that Ma is the mass flow rate of dry air, it remains constant. So Ma enters the duct and Ma leaves the duct. H0 and W0 are the enthalpy and moisture content at the inlet to the duct or inlet to the control volume, and Hc and Wc are the enthalpy and humidity ratio at the outlet, and Qt is the cooling load on the coil. Okay, we will find an expression for this, I will show you that. So this is how it can be, this process can be achieved, and if you are showing this, representing this process on a psychrometric chart, as I said, the actual process is complicated. Let us say that we know the inlet condition, okay, and we are able to locate the point on the psychrometric chart. Okay, we know the inlet point, right? And suppose we also know the surface temperature of the coil, okay, and let the surface temperature of the coil be Ts. Okay, and from straight line law we know that the exit condition always lies on a straight line joining these 2 points Ts and inlet condition T0. Okay, that means it will be lying on some line joining these 2 points. Okay, that could be somewhere here, right? So exit condition lies between TO and Ts on the straight line. The heat and mass transfer rates are obtained by applying conservation of mass and conservation of energy equations. So we take the control volume. Okay, so this is the control volume, let us say the dashed line, and we apply conservation of mass. What is conservation of mass? For example, you can write conservation of mass for dry air, which is very trivial here. For example, because the dry air mass remains constant, for dry air mass transfer equation is m dot A is equal to m dot A, whatever mass is entering, the same mass is leaving. And for water vapor also you can write the energy mass balance. So whatever mass of water is entering, the same mass of water must leave. Okay, the water is entering here in the form of vapor, it is leaving in the form of vapor and also in the form of liquid. Okay, so if you write the energy balance for it, amount of water vapor entering is m dot A into W naught. This is the amount of water vapor in the incoming stream. This should be equal to the water vapor leaving the control volume. Water vapor leaving the control volume is m dot W in the liquid form plus m dot A into Wc. Okay, so this is the mass balance for the water vapor. So from this equation we can easily show that m dot W, that is the condensate rate, is nothing but Ma into Wo minus Wc. Okay, so this is the mass balance. Similarly, one can write the energy balance, take the control volume, and for steady state whatever energy is coming in must go out, and energy coming in is in the form of enthalpy of the air, energy leaving is also in the form of enthalpy of air, and also there is some energy leaving by enthalpy of condensate, and some energy has to leave because that is nothing but the load on the cooling coil. Okay. So as I said, from conservation of mass we can show that m dot W is equal to Ma into Wo minus Wc, where m dot W is the condensation rate in kg per second. So many kgs of water is being condensed per second, that is the meaning of this. And from conservation of energy we can easily show that the load on the cooling coil Qt is equal to Ma into H naught minus Hc minus Mw Hw, and for Mw we substitute using the conservation of mass. So finally we find that Qt is equal to Ma into H naught minus Hc minus Ma into W naught minus Wc into Hw. Here Qt is the load on the cooling coil, and as I said, H naught and Hc are the inlet and exit enthalpies of air, and Hw is the enthalpy of the condensate, that means enthalpy of the liquid water that is leaving the control volume. Okay. Compared to the first term, the second term is generally small, that means this term is relatively small compared to this term. Okay. So we can generally neglect this term. Once you neglect this term, you find that Qt is equal to m dot A into H naught minus Hc. Okay. So that means simply mass flow rate multiplied by the enthalpy difference. Since the cooling and dehumidification process involves both latent and sensible heat transfer processes, one can write Qt is equal to Qs plus Ql. Okay, because we have seen that both sensible as well as latent heat transfers are taking place. So you can separate them out. So total heat transfer rate is sensible heat transfer rate plus latent heat transfer rate, where the sensible heat transfer rate is given by Qf is equal to Ma into Hw minus Hc, that is equal to Ma into Cpm into T naught minus Tc. Okay, let me show this on the psychrometric chart. On the psychrometric chart, if you see, see this is the, let us say that this is the process. Okay, so this is the process. What we are doing is we have shown that Qt is equal to approximately equal to m dot A into H naught minus Hc. Okay, H naught minus Hc is nothing but this enthalpy difference. Okay, so this enthalpy difference is split into sensible as well as latent enthalpies. For example, this is the enthalpy change during the sensible process, and this is enthalpy change due to latent heat transfer. Okay, and this plus this obviously is equal to the total enthalpy change. Okay, and in this process you can see that what is the sensible heat transfer rate? Sensible heat transfer rate is nothing but what is the temperature change? Temperature change is from T naught to Tc. Okay, so sensible heat transfer rate Qs is nothing but m dot A into Cpm into T naught minus Tc. This is equal to m dot A into Hw minus Hc. That means this portion. Okay, that means this enthalpy difference into mass flow rate. Similarly, latent heat transfer QL is nothing but m dot A into this enthalpy difference. Okay, this is the process. So that is nothing but H naught minus Hw. Okay, so like that you can split the total heat transfer rate. And the latent heat transfer rate, as I said, is QL is Ma into H naught minus Hw. H naught minus now this can also be written in terms of the humidity ratio and the latent heat of vaporization. That means latent heat transfer can also be written as Ma into HFG, where HFG is the latent heat of vaporization, into Wo minus Wc. The ratio of sensible heat transfer, why are we doing this? There is a purpose behind this. Let me explain this. the ratio of sensible heat transfer rate to total heat transfer rate is called as sensible heat factor, or abbreviated as SHF. Okay, sometimes it is also called as sensible heat ratio. Okay, that means sensible heat factor SHF is defined as QS divided by QT, where QS is the sensible heat transfer rate, QT is the total heat transfer rate, and QT can be written as QS plus QL. Now, what is the advantage of this? We will see that the sensible heat factor is an important and very useful parameter in air conditioning system calculations, and a sensible heat factor of 1 implies a pure sensible heat transfer process, because sensible heat transfer factor is 1 means QS is equal to QT, that means QL is 0, that means it is a pure sensible heat transfer process. Similarly, a sensible heat factor of 0 means QS is 0, that means it is a pure latent heat transfer process. A SHF of 0.75 to 0.8 is quite common in air conditioning practice in normal dry climate. Okay. In normal air conditioning systems, in normal dry climate, we find that the latent heat to sensible heat is in the ratio of about 1:4. Okay. That means you get a sensible heat factor of about 0.75 to 0.8. However, a lower value of sensible heat factor, for example 0.6, implies a high latent heat load such as that occurs in a humid climate, for example in coastal regions. Okay. We shall use this factor later when we do the load calculations. Okay. Now, the slope of the cooling and humidification process line is given by, what is the slope of the line? We have approximated this line, we assume that the process is taking place along a straight line. Okay, this is your surface temperature of the coil. So, the slope of the line is this. Okay, let us say Tc is the angle, then the slope of the line is tan C. Okay, and the tan C is nothing but this divided by this. Again, what is this? This is nothing but the change in the humidity ratio, that is WO minus WC, divided by this is nothing but TO minus TC. Okay. So, the slope of the line depends upon the ratio of the change in the humidity ratio and the temperature, okay, dry bulb temperature. This can also be written as, if you take a small this thing, delta W divided by delta T. Okay. So, tan C is the slope, that is equal to delta W by delta T. From the definition of sensible heat factor, now we write like this: 1 minus SHF divided by SHF is equal to QL by QS, because you can see that SHF is QS divided by QS plus QL. So, 1 minus SHF is nothing but QL by QT. Okay. Similarly, SHF is QS by QT. So, QT get cancelled. So, 1 minus SHF divided by SHF is equal to QL by QS. Now, we write the latent heat transfer rate and sensible heat transfer rate in terms of the humidity ratio and temperature difference. For example, QL is written as MA into HFZ into delta W divided by QS is written as MA into CPM into delta T. So, mass flow rates get cancelled here. Okay, this term get cancelled. Now, for HFZ and CPM we take approximate values. HFZ is written as taken as 2500 kilojoule per kg latent heat of vaporization. Similarly, the moist specific heat is approximately taken as 1.0216. Okay. So, finally, we find that 1 minus SHF by SHF is equal to 2451 into delta W by delta T. Okay. This 2451 is nothing but the ratio of 2501 divided by 1.0216. Okay. Now, from if you look at these two equations, from these two equations you find that delta W by delta T is nothing but the slope of the process line, cooling and dehumidification line. So, delta W by delta T is equal to tan C is nothing but 1 by 2451 into 1 minus SHF by SHF. Okay. So, this is the important equation. So, what does this equation tell us? This equation tells us that the slope of a cooling and dehumidification line is a function of sensible heat factor only. Okay. That means irrespective of the inlet and outlet conditions, if I tell you that a particular air conditioning process has a cooling and dehumidification process has a sensible heat factor of 0.7, okay, then immediately you can tell what should be the slope of the cooling and dehumidification line. Okay. Once you know the slope and once you know the inlet condition, then you can draw the process line. Okay. So, that is the advantage of defining sensible heat factor. Okay. Now hence one can draw the cooling and humidification line on a psychrometric chart if the initial state and the sensible heat factor are known, okay, because from the sensible heat factor you can find out the slope of the line, and you also know the initial state, and this line must pass through the initial state and you know its slope, so you can draw the process path. In some standard psychrometric charts, a protractor with the different values of sensible heat factor is provided. Okay, for example, this we will again discuss when we do the load calculations and all. So you can see that in some of the standard psychrometric chart they provide a sensible heat factor, a protractor where the sensible heat factor values are given. Okay, so different values of these lines correspond to different values of sensible heat factors. Okay, and what is the use of this? For example, let us say that my process, the sensible heat factor is like this. Let us say that this is the sensible heat factor of a particular cooling and humidification process. Okay, so the slope of the line is this, right, and let us say that its inlet state is this. Okay, now what all that you have to do is you have to draw a line through this in such a way that this line is parallel to this line. Okay, so using a protractor you can draw the a parallel line to this particular thing, and this is the process line. That means the exit condition will lie somewhere on this line. Okay, so that is the advantage of having this protractor. So as I said, the process line is drawn through the initial state point and in parallel to the given SHF line from the protractor. Of course, sometimes the value of sensible heat factor is also given on the ordinate. Okay, this again, as I said, we will discuss later. Let us discuss another important concept called as apparatus dew point temperature, or ADP. The effective surface temperature of the cooling coil TS is known as apparatus dew point temperature. Okay, in fact, the actual temperature will be varying. Actual temperature of the cooling coil will be varying because of the boundary layer development and because of the temperature gradients in the fins, etc. But we can conceptualize an effective surface temperature for the coil, because the surface temperature does not remain constant on the coil. Okay, but we can define an effective surface temperature, that means you will have a single value. Okay, and you can see on the psychrometric chart here that Ts is the effective surface temperature of this cooling coil. Okay, and this Ts is known as your ADP, that is apparatus dew point temperature. Okay, and as I have already mentioned, if you know this temperature and if you know the inlet condition, so you can draw the straight line and you can draw the process path. In an ideal situation, when all the air comes in perfect contact with the cooling coil surface, then the exit temperature of air will be same as the coil ADP. Okay, that means you have a, let us say, a perfect coil. Okay, this is this cooling coil is a perfect coil, perfect in terms of heat and mass transfers. So when this coil is perfect, the heat and mass transfer rate between air and the coil will be maximum, and you find that the exit condition will be same as, say, will be at this point. Okay, exit condition coincides with the coil ADP, right. However, in actual case, the exit temperature of air will always be greater than the apparatus dew point temperature because of various resistances. Since no evaporator coil is perfect in terms of heat and mass transfer, one can define a bypass factor BPF for the coil as bypass factor BPF is equal to Tc minus Ts divided by T naught minus Ts, or this is also equal to Wc minus Ws divided by W naught minus Ws, that is equal to Hc minus Hs divided by H naught minus Hs. Here C is the actual exit state and S is the exit state corresponding to the coil ADP. Okay, so that is shown on this figure. For example, according to the bypass factor, this thing, let us say if this is X, okay, let us say this is whole thing is Y, then bypass factor is X divided by Y. Okay, that means, or you can also define this in terms of the humidity ratios. Okay, that means this humidity ratio divided by this, or in terms of enthalpies. Okay, if you have this enthalpy, that means this enthalpy divided by this total enthalpy. Okay, so the value of bypass factor depends. A small bypass factor indicates a very effective evaporator coil. For example, if you see that the bypass factor is 0, that means the exit condition of air is same as the coil temperature, that means the effective coil temperature. Okay, so this means the coil is very effective, all the air is coming in perfect contact with the coil. Okay. So smaller the bypass factor, higher is the effectiveness of the coil. The value of bypass factor depends on the design of the evaporator coil, for example number of rows, fin pitch, etc., and also on the velocity of air. The bypass factor can be decreased by increasing number of rows or by reducing fin pitch and air velocity. Okay, so the design of the coil decides the bypass factor. In addition to that, the air velocity also decides the bypass factor. For a given coil, if you reduce the air velocity, air has more time to spend with the coil, that means more dehumidification takes place and the temperature of the air goes nearer the coil ADP. Okay. Next, let us look at another process, cooling and humidification. So, as the name implies, this is also a cooling process, but instead of dehumidifying, here we are humidifying air, that means moisture content of the air is increasing. So, during this process the air temperature drops and its humidity increases. How can we achieve this process? This process can be achieved by spraying cool water in the air stream or by bringing air in contact with a wet surface. Okay. Suppose you have an air stream and you sprinkle or you spray cold water in the air stream, or you bring the air stream in contact with a wet surface, then air undergoes cooling and humidification process. The temperature of water or wet surface should be lower than the dry bulb temperature of air, but higher than its dew point temperature to avoid condensation. Okay. This is important. You want to cool the air, at the same time you want to humidify the air, that means you want to add moisture to the air. Okay. Since you want cooling, that means there must be sensible heat transfer from air, right. That means the water or the surface temperature should be lower than the air temperature, right. That means air dry bulb temperature, but it should not be lower than the dew point temperature of the air, because once it is lower than the dew point temperature of air, then moisture condenses. Okay. So, instead of humidification, you will have dehumidification. Okay. So, to achieve cooling and humidification, we must have a wet surface whose temperature is higher than the dew point temperature, but lower than the dry bulb temperature. Okay. So, let me show this. Let us say that this is the water spray and TW is the temperature of the water that is being sprayed. Okay. Water spray means you have fine droplets of water here at a temperature of TW, and moist air is coming in contact with this water droplets. As I said, this water droplet temperature TW is greater than the dew point temperature. That means let us say that TW is somewhere here. Okay. It could be anywhere from this point to this point, okay, but not less than this point. Okay. It has to be lower than the dry bulb temperature, but higher than the dew point temperature. That is what I mentioned. Okay. Suppose it is somewhere at this point, right. Then what happens? Since its temperature is lower than the air temperature drops, and since its partial pressure or vapor pressure is higher than the vapor pressure of air, some moisture evaporates from the water droplets and moisture is added to the air. Okay. That means air gets humidified, and from straight line law we know that if you know this point and the inlet condition, the exit condition must lie somewhere here on this line. Okay. So, you can see that the process will be somewhere along this line or along this line depending upon your temperature. Okay. So, what is happening? The temperature is reducing, at the same time moisture content is increasing. Okay. The moisture content is going up, right. So, this is the cooling and dehumidification process. So, what is the practical application of this process? The evaporative coolers are what is known as desert coolers, and cooling towers are based on this process. That means, in evaporative coolers and cooling towers, the air undergoes cooling and humidification. Of course, in evaporative coolers or desert coolers, we need to cool and humidify the air. That means air is important to us, but in cooling towers water is important to us. We need to get cold water from the cooling tower. During cooling and dehumidification, there is sensible heat transfer from air to water and latent heat transfer from water to air. Okay. Obviously, you are reducing the temperature of the air, at the same time you are increasing the humidity ratio of the air. Okay. That means, since you are reducing the temperature of the air, that means sensible heat transfer is taking place from air to the wet surface. Okay. Whereas latent heat transfer, because moisture is added to the air, latent heat transfer is taking place from the wet surface to the air. Okay. That means the direction of sensible and heat transfer processes are opposite. The total heat transfer depends upon the water temperature TW. Okay. This is very important. For example, the enthalpy of air increases if water temperature is greater than the WBT, that means if it is greater than the wet bulb temperature. That means if you are spraying water, or if you are bringing air in contact with the wet surface whose temperature is lower than the dry bulb temperature but greater than the wet bulb temperature, then you find that the enthalpy of the air increases. That means there is net heat transfer to the air. Why there is net heat transfer to the air? You will find that the latent heat transfer to the air is higher than the sensible heat transfer from the air. Okay. So, as a result, there will be net heat transfer to the air when the water temperature is higher than the wet bulb temperature. Okay. In the reverse case, the enthalpy of air decreases if water temperature is lower than the wet bulb temperature. The process of adiabatic saturation, we have discussed this process in the last lecture. This adiabatic saturation process is a special case of cooling and humidification process during which the wet bulb temperature remains constant. Now, let us look at another process called heating and humidification process. During winter, it is essential to heat and humidify the room for comfort. Okay. So, this is basically required in cold countries for winter air conditioning systems. Okay. So, you have to heat and humidify the air, that means you have to increase its temperature and you also have to increase its moisture content. This requires supply of air that is heated and humidified. Okay. That means both sensible and latent heat transfers are involved again. This is normally done by first sensibly heating the air and then adding water vapor to the air. Okay. That means you have a heating coil here. Okay, so this is your heating coil or simple heater. Okay. So, air first flows over the heating coil, for example like this. So, its temperature increases, that means this is a sensible heat transfer process. Okay. So, at this point, but that means after this you add, let us say, steam, okay, or some water vapor. So, it undergoes a latent heat transfer process. Okay. So, the process is like this. Okay. So, the combined process is something like this, right. So, this is the heating and humidification process. So, from energy balance, total heat transfer rate is, again, if you can apply the energy balance to the control volume, okay, take the control volume and apply energy balance to this, the total heat transferred during this process is given by this equation, QH is equal to MA into HD minus H0 minus MW HW, where HD and H0 are the exit and inlet enthalpies of air, MA is the mass flow rate of dry air, MW is the mass of water added, and HW is the enthalpy of water. Okay. Next process is heating and dehumidification process. Okay. So, here temperature increases, as the name implies, at the same time moisture content reduces. This process is also called as chemical dehumidification. It can be achieved by using a hygroscopic material, that means a material which has affinity for water, okay, which absorbs or adsorbs the water vapor from the moisture. Okay. So, this is the, for example, we have some hygroscopic material which could be either solid or liquid with an affinity for moisture. Okay. It could be a solid or liquid. So, when air comes in contact with this solid or liquid, since this has affinity for moisture, it will absorb the moisture or adsorb the moisture from the air. So, as a result, moisture content of the air reduces. And if you assume that this process is taking place adiabatically, that means everything is perfectly insulated, then this process will be taking along a constant enthalpy line, that means enthalpy remains constant. Okay. So, you can see that during this process the humidity ratio, okay, if this is inlet and this is outlet, humidity ratio is reducing. Okay. At the same time the temperature is increasing, that means T0 is greater than Ti. Okay. So, this is the example of chemical dehumidification or heating and dehumidification process. Okay, this I have already explained. So, the hygroscopic material could be, for example, a solid such as zeolite or a liquid absorbent. Now, next let us discuss another important process called mixing of air streams. This is a common process in air conditioning systems. Okay. So, mixing may or may not lead to condensation of water. Okay. So, what is this? Let us say that we have two air streams, air stream 1 and air stream 2. They are adiabatically mixed, that means this is a perfect insulation, perfectly insulated duct. Insulated duct. Okay. So, simply we are mixing the air streams and we would like to find out what is the exit condition. right. So, since this is an adiabatic process, let us say that this is the state 1 and this is the state 2. Okay. So, air at this condition with certain mass flow rate, let us say m dot A1 and m dot A2 is the mass flow rate of the air stream 2. These two air streams are getting mixed and you get a resultant air stream with the mass flow rate m dot A3, that is equal to m dot A1 plus m dot A2 from mass balance, and at a state point 3, that means you have temperature at the exit T3, humidity ratio W3, enthalpy H3, like that. Okay. So, there is no condensation or anything during this process. So, from mass balance you can easily write, this is the mass balance, what I have written is for the mass balance for the water vapor, MEA1 W1 plus MEA2 W2 is the amount of water vapor coming into the duct, that is equal to the amount of water vapor leaving the duct. All these equations are for steady state. Okay. So, this is equal to MA3 W3, where MA3 is nothing but MA1 plus MA2 into W3. Okay. Similarly, from energy balance, if you do an energy balance, you can write that MA1 H1 plus MA2 H2 is equal to MA3 H3. Okay. That means energy coming in is energy going out. So, that can be written as MA1 plus MA2 into H3. Thus, the exit condition depends on the ratio of mass flow rates of incoming air streams. Okay. For example, using the two equations, you can show that MA1 divided by MA2 is equal to, for example, if you are writing in terms of humidity ratios, or this can also be equal to H2 minus H3 divided by H3 minus H1. Okay. So, you can see that the exit condition depends upon the ratios of the mass flow rate. For example, when MA2 is 0, when MA1 is 0, let us say MA1 is 0 means W2 will be equal to W3, that means this point is nothing moves to towards this point. Similarly, when MA2 is 0, W3 will be W1, H3 will be H1, you have so this point. Okay. So, as the mass flow rate of one or other air stream increases, this point shifts towards that air stream. Okay. If this air stream has a higher mass flow rate, 3 will be closer to 1. Okay. A reverse case, if this is higher mass flow rate, 3 will be closer to 2. When the mass flow rates are same, 3 will be the midpoint. So, this is the process without condensation. You can also have a process called mixing with condensation. Okay. This happens when large quantity of cold air mixes with warm air at high relative humidity. Some amount of water vapor condenses. Okay. For example, you have a special case, again this is a mixing process. Let us say that incoming air 1 is very cold. Okay. Temperature is very low. This is mixing cold air, okay, is mixing with hot and humid air, that means 0.2. Okay. So, the mixer condition must lie on the straight line joining these 2 points. So, if when you join the straight line, these 2 points by straight line, you find that the resultant condition is in the 2-phase region. Okay, because this is a 2-phase region. Okay, that means it's an unstable this thing, and the liquid droplets must separate out. Okay, so liquid droplets will be separated from the air stream. As a result, its humidity ratio reduces. You find that finally the exit condition 0.3 will be exit condition of the air, that is will be at this point. Okay, that means at a lower humidity ratio. Hence, the humidity ratio of the resulting mixer will be less, and there will be an increase in temperature of air due to the release of latent heat of condensation. Okay, temperature increases, humidity ratio decreases. This process rarely occurs in air conditioning systems. You normally do not encounter this process. However, this is the phenomena which is behind the formation of fog or frost in winter. Okay. Now, let me quickly describe what is known as an air washer. An air washer is a device for conditioning air. In an air washer, air comes in direct contact with a spray of water, leading to an exchange of heat and mass between air and water. Okay. Let me show this. So, what we have, this is the air washer, we have a water sump, this is the water. Okay. So, this is connected to a pump, a cooler or a heater. So, water is taken from the sump, it is either cooled or heated, and it is again sent back to the air washer, that means it is sprayed. Okay. You have a spray of the same water is sprayed after conditioning it. Okay. So, the air enters this air washer through these drift eliminators, which eliminate the, of course, you do not require a drift eliminator here, you require it at the exit. So, air enters let us say through a filter, and it comes in contact with the spray of water, and during this contact either sensible or latent heat transfer takes place or both take place, okay, depending upon the temperature of the water, right. So, by controlling the temperature of the water, that means this water temperature, you can achieve different exit conditions, okay. So, this unit is known as an air washer. The outlet condition of air depends upon the temperature of water sprayed in the air washer. Hence, by controlling the water temperature externally, it is possible to control the outlet conditions of air, okay. Thus, an air washer can be used for both summer and winter air conditioning system. That means the same system can be used for cooling and dehumidification in summer and for heating and humidification in winter by controlling the temperature of the water. Let me just give an example quickly. For example, in an air washer, one can achieve cooling and dehumidification by circulating water whose temperature is lower than the dew point temperature. Since there is a transfer of enthalpy from air to water, air gets cooled and water gets heated up, okay. So, water has to be externally cooled, okay. Here both latent and sensible heat transfers are from air to water. The reverse process, heating and humidification, you have to spray the water whose temperature is higher than the dry bulb temperature. Here both sensible and latent heat transfers are from water to air, hence water has to be heated externally, okay. In the first case water has to be cooled, the second case water has to be heated. Then you have adiabatic saturation process. Here all that you have to do is simply recirculate the water. Here the sensible heat transfer from air to water is exactly equal to latent heat transfer from water to air, hence no external cooling or heating of water is required. That means this is a case of pure water recirculation, okay. And the last process is cooling and humidification. Here you have to spray the water whose temperature is higher than the wet bulb temperature but lower than the dry bulb temperature. Here the sensible heat transfer is from air to water and latent heat transfer is from water to air, but the total heat transfer is from water to air, okay. That means water has to be heated externally, okay, because it is losing energy, so you have to heat the water externally. This is an example of a cooling tower, okay. In a cooling tower this is what happens, right. So, like that, by controlling the water temperature, that means by controlling the cooler or heater, you can achieve the required condition at the exit of the air washer, okay. So, that means an air washer can be used as an all air air conditioning system, okay. So, at this point I stop this lecture and we will continue this in the next lecture. Thank you.